So the very last thing we're going to talk about is an Euler circuit. So we're going to start with the definition for that. Let G be a graph and an Euler circuit for G is a circuit that contains every vertex and every edge of G. So just to kind of remind you what this all involves, this needs to start and end at the same vertex in order to be a circuit. It uses every vertex at least once. Remember that a circuit has to have at least one edge, but in particular this Euler circuit says it needs to uses every edge exactly once. So the question becomes, if I have a graph, how do I know if it has an Euler circuit or not? So one thing that can help us a little bit is this theorem. In your book it's 10.1.2, and it says if a graph has an Euler circuit, then every vertex of the graph has positive even degree. So what I want us to do is to take this theorem and look at the contrapositive of that theorem. So remember, when you find the contrapositive, you flip it and you negate each piece. So you need to negate every, so remember that's the universal quantifier, so it becomes the existential if some vertex of a graph, and the opposite of even is odd, has odd degree, then the graph does not have an Euler circuit. So let's look at an example. Let's look at a graph with 4 vertices. V1, V2, V3, and V4. And I'm not going to label the edges just yet. I'm going to connect those two and those. And I'm also going to have an edge here as well. So if I look here, I have vertices that have odd degrees. In particular, V1 and V3 have odd degree. And so I know by that contrapositive statement, by the contrapositive of Theorem 10.1.2, 2, the graph does not have an Euler circuit. And I want to end kind of this section with the following theorem. Theorem 10.1.3 says if a graph G is connected and the degree of every vertex of G is a positive even integer, then G has an Euler circuit. So if your graph is connected and all the vertices have positive even degree, then you will have an Euler circuit.